Today, we're going to be going over a testing methodology and preliminary data for my new CFM cubic feet per minute airflow test apparatus, and explaining the science behind why I've chosen to do a test this way and that sort of thing. So let's get into it. So first things first, you'll notice I got two different sizes and a whole bunch of different adapters. So the small one over here is for 120 down to a really small 40 millimeter size fan. The back is the size of my anemometer, so it's got that grid pattern to streamline the airflow as it goes through it, so that I should get more consistent results, especially when we're looking at reverse blade fans. And it's just got the pins on it, so I can line it up, the edges, and get the airflow going through it. And it's got that little bit of cone-shaped shape. And then we have the bigger one. So I'm sliding over my panels. So this one can hold up to 200 millimeter class fans down to 120 millimeter fans. Again, with that cone shape, it's long enough that the airflow has plenty of time to stabilize with, again, the grid in the back. And it's got the same sort of thing with different adapters to fit over it and get the applicable size testing going for it. So now that we've taken a look at this, let's look at the science behind why I'm doing it this way, and then we'll look at some of the preliminary data and fan ranking. So the ranking in that section is going to be this by itself, meaning the performance going through it, as well as comparing to my original CFM test. So hopefully they trend the same way. All right, now we're on to the explanation of the design. This is a CAD model of it, and the general scientific explanation of what my thought process is behind this test. So it is a cone shape. This beam right here is basically just to stabilize it. It's got a little bit of a grid in the back to help streamline the air as it exits and into my anemometer, which would sit right at the back. This opening would be able to fit up to 200 millimeter sized fans, so it's quite large. All right, so a very simplified view of how fans, well, push air. So you have, generally speaking, static pressure fans, which kind of blow air off to the sides, or I say badly optimized fans. You're gonna have to ignore this radiator and device over here, but very wide dispersal of air. So in other words, it doesn't blow very fast or very far. And then in the top picture, we have more airflow focused fans, which tend to have a more concentrated airflow, and it gets from point A to point B without dissipating as much. Through my testing and my case simulation test, which I'm going to go over, it takes into account this information, and this test is sort of supposed to be a halfway in between the case simulation and my CFM type test. So CFM just being cubic feet per minute, so volumetric flow rate. Now, different types of tests. Standard CFM, again, volumetric flow rate type tests. You have a fan, you got a tube or a box. Well, actually, no, in this case, it is a tube. Air in, CFM, open back, same size as the tube. I run this test for both 120 and 140 millimeter class fans already. There's basically no room for the air to expand out off to the side, so the air just goes push straight out the back. Tube style CFM testing, the fan will blow air down the tube. The air exiting the back of the opening, airflow allow the CFM to be calculated. Airflow pattern does not matter much because it's all being pushed down. There's no room for it to expand off to the side. There may be some general trends though, but generally speaking, it matters significantly less. Like I said, probably less than 1%. This style test, you need a dedicated tube size for each fan size tested for it to operate as expected. And the second style is more like a box. The box is bigger than the fan, so you have it optimized for whatever size. And then you have an outlet, an orifice, if you will, at the back, and you have it as a, quote, unrestricted size. So it needs to be a specific size for the size of the box to be considered unrestricted, so the air would travel in and out evenly. So you don't care about how the air is doing inside the box at all. You just care about how fast the air is coming out the back. So in other words, the orifice, whatever size this is in the back, the air will build up kind of inside of it, and then the air will just kind of blow through out the back, and you would measure the airspeed that it's coming out the back because you're in a way pressurize the box, and then the air wants to escape as cleanly as possible. So you would have that sized, how do I explain this in a way without going too scientific? It needs to be sized in such a way to be considered unrestricted. Otherwise, it would become a restricted airflow, and that's how you generate your PQ curves. Did I cover everything on there? Opening allows you to calculate CFM. Airflow patterns do not matter because you're only looking at the outlet. One box size fits all or most fans, but must be long enough or orifice not be in direct line of airflow path. So in other words, kind of at the top or something like that. So or this box needs to be long enough so that the airflow generated by the fan doesn't really matter. So its airflow patterns don't really matter. CFM is just volumetric flow rate if unrestricted in this kind of use case. I think I covered everything on here. Where do I cover my CFM test? At the back. Now on to my new testing. Same test apparatus for multiple fan sizes, from 120 millimeter to 200 millimeter fans in size. And the smaller one, is designed for 120 millimeter down to 40 millimeter class fans. So in other words, absolutely tiny ones. Most cases are designed for 120 to 140 millimeter fans, but the largest fans most cases can fit are 200 millimeters, and on average I find that from the case wall to the kind of glass, most cases seem to be at about 180 millimeters, that vertical distance. So think about like how tall a CPU block cooler it could fit as that scenario. So 200 millimeter class fans, but most realistically can hold 180s without restrictions. This test allows for multiple size fans to be used to directly compare them against each other to show the effectiveness of a specific fan against one another. Larger fans will more easily fill the internal volume of the apparatus. So that is a limitation with this test, as demonstrated over here. 120 will blow up and have room to expand out, while 200 millimeter fans will basically be filling the whole space and just blowing directly down the tube, which realistically you'd see in most computer cases. This test, in theory, allows for airflow to come out of the fan to be taken into account. So in other words, what is the quality of that airflow? Is it spewing off to the sides, or is it a direct airflow path? The test should also fit halfway in between my case airflow and a true CFM test. That is how I envision it. And hopefully it kind of works that way, because you're going to have these stall points up here. So if a fan blows off to the side, it will fill this area with kind of junk air. But then again, it might fill it with junk air, and then it would streamline itself and blow down. I don't have CFM software. I don't have computational fluid dynamics software to run a simulation. I can only design a test and, well, use it as my test apparatus. So along that same line, so non-focused airflow versus focused airflow. More speed loss, lower CFM. So in other words, it will spread out the air coming out of it, and it'll be less direct flow down it, having these voids basically where it expands the air and then it kind of moseys on down the path. While a more direct airflow will kind of, yes, this looks larger and there'll be essentially vacuum in there, but the air should concentrate down the tube and be focused in there. Again, this is how I envision it, where the yellow is reflected air, so coming off and then gets reflected down, while the red line would represent air coming directly from the fan. And, well, I'm hoping that it'll work this way. Either way, in testing, you just need to keep everything consistent to generate quality data, even if it's not testing what you hope it's testing. So the only way to know is to generate lots and lots of data about both static pressure ones I know shoot air off to the side and ones that have a focused airflow pattern. And then lastly, my case simulation airflow test. This test is designed to more directly simulate a PC case, open back and able to fit up to 200 millimeter class fans. Airspeed is measured at fixed intervals down the box to show how airspeed drops with distance from the fan, similar to how it is in a computer case. It also shows that more focused airflow will maintain a higher airflow further down the box than a less focused airflow. This test does not show CFM, because airflow at the top and middle and bottom are all different. I'd need to fill that entire volume, or have many anemometers and take many readings from each location to average out the airspeed and then calculate the CFM. I would need a test orifice to measure airspeed through to determine the CFM, or average multiple speed readings at each of the distances, like I just said. This test is used to determine the quality of the airflow coming out of the fan. This test allows me to directly compare multiple fan sizes against one another. Larger fans generally do better because they more easily fill the volume, but also show the quality of the airflow. As a second note of this, you can get the same amount of air total volumetric flow rate by having more smaller fans. So, but then you have to balance out air, like 2 fans running at wouldn't be able to spin as fast as one. No, I'm saying that wrong. 1 fan to create, let's say, 3 meters per second of air. So 2 fans to generate 3 meters per second of air would spin slower, but may not generate less noise, if that makes sense, because there's now 2 of them. And that's where kind of some testing comes in. And along that same line, those 2 fans then comparing to larger diameter fans. So this can create a huge testing rabbit hole. So, I do what I can. All right, I've rambled a lot. As an aerospace engineer, I have a firm belief that there's more than one way to test products and that multiple approaches should be taken to account for multiple aspects of a product, particularly fans, and in computer cases, which are ironically very complex to cool. As a result, I test fans multiple ways to allow the user to see a good, complete picture of how good or bad a product is, in this case, is a fan. So that's why I test all these different ways to try to allow you, the user, to make as informed a decision as possible. Now, this is comparative data. It's comparing my original CFM test for 120 millimeter fans only versus the new test with only 120 millimeter class fans. The value difference between the blue and the red doesn't matter. What matters is kind of the rank order to see if they generally line up the same. And as you can see, there are some outliers, like the Apex Stealth is an outlier. It should be positioned quite a lot higher if we were using the CFM test as the main one. But in the new CFM test, in the conical shaped tube, it is positioned quite a bit lower at 10.5 decibels. But overall, the trend is similar, but it's not exactly the same. So we got the Mega Cool, the TL-S12S, the A12X25, the P1. I haven't tested all the fans that I tested. This is the fans I had available and ones that I wanted to have as comparison standpoints. And this test will be going forward I will be using this test going forward on all my testing. Then we have the 17.5 decibel reading. And again, we have some outliers. The A12X25 should be ranked higher, but it's ranked below the P1. Then you have the Mega Cool, the TL-S12S, Apex Stealth, but generally speaking, it has the correct trend down that my original CFM test is sort of accurate, or trends about the same. But going forward in future testing, so revision 3, which I keep talking about, but I'm not quite there yet. I need more viewer support, unfortunately. I put a little grid pattern inside my CFM tube to streamline the airflow. I did an experiment where I stuck it in there and took airflow readings, but it actually dropped my air speeds too much that I couldn't equate it. So as a result, I can't do that going forward. So I have to leave it as an empty tube, which does mean that it's not as good a test as it otherwise could be. Not saying it wouldn't affect these results, though. CFM comparison at 800 RPM. The CF-V12HB, my oldest fan, the Cougar, is kind of the best at 800 RPM. Then we got the Mega Cool, the X12F, the P1, the A12X5 is down here next to the TL-S12S, which is surprising. This doesn't take into account noise. This is just pure airspeed versus RPM, okay? And the reverse blade one, well, look at that improvement. It is because my original test, the air was not streamlined, and it would screw up reverse blade fans, or fans that blew air or rotated in the opposite direction. So I'm glad that this test is fixing it. I should have noted that in an earlier one, though. At 1,500 RPM, this one is more of a mixed bag. For the original, comparing against the original CFM test, while you see a nice trend with, the new test, when comparing a bunch of these fans. And then at 2,000 RPM, the blank spaces are just because those fans don't spin at 2,000 RPM, if you're wondering. We got the Mega Cool at the top. Then we got the P1, the X12F, the A12X25. So this, again, is showing relevant data. And then at 100% PW fan signaling. And the trends do hold, which makes sense because this is the fans at 100% PW fan signal, not locked into specific RPMs. So it's kind of a useless test, or useless chart in a way, but it does show you the maximums that these fans can kick out and how they would rank as such. So kicks and giggles there. And that does bring us to the end of this video. I do thank you for joining me. I hope you're all looking forward to this new data, and I'm really looking forward to that new test apparatus. Hopefully I can get some time to buy some smaller fans, because well, there are specialty cases that use 40, 80, 60, 92 millimeter fans, but there don't see very many tests on it. Probably because they aren't as common, but regardless, I do want to be complete testing, just to kind of show the differences with kind of everything. Anyways, thank you very much for joining me here on Computer Tech More for this intro into this new testing methodology, and kind of how it will be done. Anyways, thank you very much for watching. Have a great day, and I'll see you next time.